We hear all about the amazing power of AI literally every single day. But what if I told you that its incredible ability to learn, to see, and to understand our world, all of that hinges on just one tiny, often overlooked component? Well, today, we're going to go inside the brain of AI to find that exact secret ingredient.
So, at the very heart of modern AI, you've got these things: artificial neural networks. They're these super complex systems of interconnected nodes, and yeah, they're totally inspired by the human brain. These things are behind, well, pretty much everything, from driverless cars to the apps on your phone. But here's the thing: the real magic isn't in this giant, sprawling network you see. Nope. It's what's happening inside each and every one of these tiny little nodes. So, what is the secret?
Okay, so to get our heads around this whole massive network, we've got to zoom way, way in. We need to understand its single most fundamental unit, the neuron, or as you'll hear it called a lot, the node. All right, the first thing that happens inside a node is honestly surprisingly simple. It takes in a bunch of inputs. For each one, it decides how important it is. That's called a weight. Then it just multiplies the inputs by their weights, adds them all up, and then tacks on one final number called a bias. And that's really it. It's just a weighted sum. But, and this is a huge but, here's the catch. If that simple little calculation was the whole story, then these neural networks, I don't care how massive you build them, they'd run into a really serious limitation. It's something we call the straight line problem. You see, a network that's only built on these simple, weighted sums can only ever understand straight line relationships. Imagine trying to describe our world, with all its complex curves and shapes, using only perfectly straight rulers. It just wouldn't work, right? You'd miss all the nuance, all the complexity that really makes the world what it is. This quote here from Wikipedia, it just hits the nail on the head. It basically says that if all you do is keep stacking these simple, straight-line calculators on top of each other, you don't actually get any smarter. A 100-layer network is no more powerful than a network with just one layer. It's still just one big, dumb, straight ruler. So how do we break out of this straight-line prison? What's the escape plan? Well, we need a spark. A non-linear spark, and that's what gives the network its real power. And here it is. This is our secret ingredient, the activation function. So after the node does that first simple calculation, the weighted sum, the result gets passed through the second, absolutely crucial function. Think of the activation function like a gatekeeper. It looks at that result and it gets to decide the node's final output. It's the one that determines if and just how strongly that neuron should fire. Okay, and this is where the real magic happens. The absolute most important property here is nonlinearity. This is the thing that shatters the straight line problem. It lets the network finally learn all the curvy, complex patterns of the real world. In fact, this is the key to something called the universal approximation theorem, which is wild. It basically proves that a simple two-layer network can learn to approximate pretty much any function you can imagine. And that last point, continuously differentiable, that's super important too. All it really means is that the function is smooth, with no sharp jumps. And that smoothness lets the network make these tiny, smart adjustments as it learns from its mistakes. It's the key to making the training process actually work efficiently.
All right, so now we know why these things are so critical. Let's meet a few of the most famous ones, the activation functions that have really shaped the history of AI.
First up, we've got a real classic, the sigmoid function. The best way to think about this one is like a smooth dimmer switch on a light. You can give it any number, positive, negative, huge, tiny, doesn't matter, and it'll gently squash it down into a value somewhere between 0 and 1. For a long time, this was the go-to for early networks, especially when you needed an output that looked like a probability. But these days, the undisputed champion of the modern era is ReLU, which stands for Rectified Linear Unit. And what's just so amazing about it is how radically simple it is. Get this. If the input is negative, the output is 0. End of story. And if the input is positive, the output is just, well, it's the input. That's it. It's like a simple hinge at 0. So let's put them side by side. On the left, you've got sigmoid's classic S-curve. See how smooth it is? And its output is always neatly tucked between 0 and 1. It was great for those early models. But then on the right, you've got ReLU's sharp hinge right at 0. Its output can go from 0 all the way up to infinity. And it's this radical simplicity, this super basic hinge design that makes it ridiculously fast for computers to calculate. And that raw efficiency, that's exactly why it became the default choice for the massive, deep neural networks we're building today. And of course, there's a whole family of these functions out there. You've got the binary step function, which is the simplest you can get, just a pure on or off switch. But that sharp edge actually makes it kind of hard for networks to learn with. Then you've got sigmoid, the smooth operator we just met, and ReLU, the modern efficient standard. And you can even see there are more advanced versions like GLU, which you can kind of think of as a smoother, slightly more sophisticated take on ReLU. And that little bit of smoothness is why it's a favorite in some of the most powerful AI models running today.
So, okay, this is all cool math, but why does it matter? Well, these functions aren't just some abstract curiosity you'd find in a textbook. No way. They are the engines, the literal engines, that have powered the biggest breakthroughs we've ever seen in artificial intelligence.
Just take a look at this timeline. Back in 2012, this model called AlexNet used the super fast and efficient ReLU function, and it completely changed the game in computer vision, overnight. Then in 2015, another model, ResNet, also used ReLU to build networks that were way deeper and more accurate than anything that came before. And fast forward to 2018, you have Google's groundbreaking BERT model. It used that fancier GLU function to reach a whole new level of understanding human language. Every single one of these giant leaps forward was enabled by choosing the right activation function.
So when you boil it all down, it really comes back to this. Just one component, that single nonlinear function tucked away inside each tiny node, that is the difference. It's the difference between a simple calculator that just follows instructions and an AI that can actually learn, create, and even reason about the world around it. So think about it like this. If activation functions are the tiny little switches that allow these networks to think, what will the next generation of these switches even look like? As we keep pushing AI to be smarter, faster, and more creative, what new mathematical spark is going to be the secret ingredient for that next great breakthrough?